today. Oh, I bet this isn't recording.
Hey.
Nope, it is. All right, I want to start now. So, let's start at the back of the packet. I think that'll be a good idea. So, start on page 12, number 15.
Wait. Is it quiz 5 or 2?
Yep. Yep, the last page. The very last page. Just flip it over. All right, so we're starting at the last one, so things are going to get easier as we go forward, right? So like this one is real easy. So I'm sorry that's going to start out hard. They're actually not that bad. No proofs required. It's just finding letters. 12, the last page. Amazing. Fourth hour has all of announcements, and yet we still start later than every other class. All right. Let's rock and roll. Do you need another one, Katie? I would highly encourage you not to write stuff down, because I do this entire packet online in a video.
Can we take a picture of it?
Sure. Watching in real time just works better. All right, so G is the circumcenter. Well, if the circumcenter is on the triangle, right, then what kind of triangle must ABC be? A right triangle. So that's a right angle. So that's something. These are all right angles. So we have a lot of right triangles. If you have right triangles, you should be thinking Pythag and or similar triangles, right? For this, we're just going to do Pythag. So, also, what kind of lines make the circumcenter? What kind of lines form the circumcenter? Yeah. Good. So these aren't just perpendiculars then. They must also be bisectors, right? So they're going to bisect these sides. So these sides are the same, which means that's a 6. And these sides are the same. So that's useful to know. Also, circumcenter. Why do they call it the circumcenter? Circle that goes around the triangle, right? So there's a circle that goes around the triangle, which means that these segments here, let's use orange, that's from the center to the circle, right? So that's a radii. Isn't this also from the center to the circle? And isn't this also center to circle? So those are all congruent. So that's 10. What's Z? 10. If you know your crap, these are really easy. If you don't, they're really hard. My idea is I set the bar low for these ones because I want it to boost your grade. Because this is important to understand, right? It shows understanding. And I love putting questions on quiz that are easy if you know your crap and really impossible if you don't. But the problem is I set the bar low thinking that you guys can walk over it easily, right? And what do? You trip. Okay? Let me set the bar low for easy stuff. And don't trip over it. Because then it just screws you over more. Okay? Take the easy win. Z is 10. Okay? How are we going to figure out X? Well, it's a right triangle, isn't it? Don't I know one of the legs and the hypotenuse? How do I know that's the hypotenuse? Because it's across from the 90, right? So I know the hypotenuse and a leg. How can I figure out the other leg? Yeah. Most famous theorem in all of mathematics. The most famous theorem in all of mathematics. Something you can do with right triangles? Come on. The Pythagorean Theorem, right? So x squared, don't be afraid of guessing. It's totally fine to be wrong. Now, z is the hypotenuse, right? So that means it goes in for c, right? The hypotenuse always goes here. Don't think, oh, variable, I'm going to stick it here. Not true. X is a leg, so it goes for either A or B. Okay? So x squared plus 36 equals hundo. And if we subtract, we get 64. So x must be what? What's the root of 64? 8. So x is 8. Cool. Well, this is kind of the big brain play. If this line is 6 and I go straight across to this line, isn't that also going to be 6? And it's a rectangle, right? So that's going to be 6 as well. Nope. I set the bar low. So if that's 6 and that's 10, what does this have to be? 8. Same idea, right? This is 8. That's 8. It's just Pythag again, right? You could do Pythag. 6 squared plus we don't know squared equals 10 squared, right? 10's the hypotenuse, so it goes here. Right? 6 squared plus we don't know squared equals 10 squared. It's going to be 8, right? So if both of those are 8, what's y going to be? 16. You want these on your quiz tomorrow. Yes, you do. Part 2 and part 1 combined. Yep. Take a snap. Yep. Selfie.
Which part do I take tomorrow?
Both. Everybody gets both.
Yeah.
We're grading it on Wednesday.
What do I count me? Do I still count me being gone for the day? Do I still
If you were absent for the quiz, would you grade your quiz in class? No, because you wouldn't be here. Right? Imagine you're absent on a Friday. We grade it on a Monday. Would you grade your quiz in class? No, because you're absent. So you're not going to grade it when we do in class. Right? So you have until Friday morning to complete it, because I have to get the grade in the grade book. Although you don't know that you can put it on quarter 3 or quarter 4. It's your choice. Awesome.
There's for like quiz 4, I have to.
Great. We'll talk about that later. Collective right now. 14. Flipping forward in the packet. Again, the further we go, the easier these actually get. The first 2 that I showed you are kind of difficult. But they're actually not hard. They're just weird, right? There you go. So, what kind of center must G be? In center, because it's the center of an inscribed circle. Now, circles always have radii. Isn't this a radii? And isn't this also a radii? And wouldn't this also be a radii?
Yes.
So they're all 5. Again, if you know your stuff, this is really easy. So that's a right angle, because whenever we measure distance, we measure perpendicular to the object, right? You wouldn't be like, look, the distance from G to this side is this. No, you'd measure straight down, right? Straight across. So same thing here. I would measure straight across. So this is 90, right? And here would be 90. Remember, the in-center is equidistant from the sides of the triangle. It's the same distance from every side, which is why you get a circle in here, right? The same distance from every side. So those are all 90. We've got 90-degree triangles. What should we be looking for? The most famous theorem in all of mathematics. Pythag, right? So if I want to figure out y, is y the leg or the hypotenuse of this triangle? Leg. Exactly. Yeah, that's right, like your mom. All right, so we know a leg. We don't know the hypotenuse and we don't know the leg. So we can't do Pythag to figure that out because there's not enough. But isn't this right triangle sharing the hypotenuse? So we can do Pythag here and figure out this right triangle's hypotenuse. And then we get this guy, right? So how do I figure out the hypotenuse here? Well, I do 5 squared, because that's a leg, right? Plus root 21 squared, because that's a leg. And you're like, oh, roots, ew. It's totally fine. Equals we don't know leg. Okay, let's do this in orange. Or we don't know hypotenuse. We'll call it h. Right? We're going to figure that out. Because then when we have that, then we can get these two. So what's 5 squared? 25. Only thing funnier than 24. What's root 21 squared? 21. Roots and squares cancel. You love roots. Roots are good.
Roots.
So 3 times 7 is 21. The limit does not exist. All right. So that means h must equal what? Ew, it's fine. It sounds like a fun place to be. Route 46, fun place to drive. Yeah? You good? Okay. Cool. So, if we know that's Route 46, now we can do Pythag over here. Is that the hypotenuse or a leg? Hypotenuse. So it's going to be 5 squared plus y squared. Don't assume variable means it goes over here, right? It's a leg. So it's either A or B, your choice. The y goes here because it's a leg. A and B are always the legs. C is always the hypotenuse, right? Now, if you're clever, you'll realize that these two triangles are congruent by hypotenuse leg. They share a hypotenuse and they have the same legs. So if this is 5 in Route 46 and this is 5 in Route 46, that's Route 21. What does this have to be? Route 21. Now, if you didn't know that, you do Pythag, and it would end up being Route 21. You get 46 minus 25 is 21. You root both sides of Route 21. Is it funny?
What's 9 plus 10?
Oh, it's a meme? Yep. Wow, I bet it's a good one. All right. Check out these two triangles. Don't they share a hypotenuse?
Which one is it?
Don't they share a hypotenuse? And don't they have congruent legs? Then by HL, they're congruent. So if this is 5 and 12, this is going to be 5 and 12. Now, if you didn't see that, do the same thing you did here. Figure out what this hypotenuse is, right? What's 5 squared plus 12 squared? Well, whatever it is, it's going to be this guy squared, right?
You make me giggle.
Right? Are you with me?
Sorry, I got in everybody's way with my colossal body.
Mark, clean up your stuff and shut up. So, up here, the legs are 5 and 12, right? And it's a 90 degrees, so I can do Pythag. 5 squared and 12 squared will get me the hypotenuse squared. What's 5 squared and 12 squared added together? 25 plus 144. What's 144 plus 20?
164.
Add 5?
69.
Nice. I make my own homework. And 169 rooted is 13.
That's my age.
Yikes.
Just kidding. I'm 15.
Still yikes. Good lord.
I'm 16.
Yikes. 5 squared plus 12 squared equals 13 squared, so x will be 12. Right? All right. 13. How many triangles do you see? 2. Is this a triangle?
No.
All right, I warned you. You're going to do it anyway.
Not 3 angles.
All right. We know that vertical angles are congruent. I'm sorry, not vertical, cap, right? Corresponding parallel angles. So these are congruent. And then they also share angle A. So what do we know about these two triangles? They are similar, right? By double angle. In this case, we have 3 angles, which is overkill. But they're similar. So small triangle is similar to the big. If you want, it might help to write the similarity statement. AED is the small triangle, yeah?
They have those in our schools.
A. Today is not the day to try a comedy career. All right. A in the small triangle is going to go with what in the big triangle? A, right? Because they share it. E in the small triangle is going to go with what in the big triangle? C. And D in the small triangle is going to go with B in the big triangle. Now, this will help you match stuff up. AE is 9, right? And it should go with AC. What's AC's length? 12. Thank you. The whole thing is 12. You have no idea how many people said 3. 3 is not part of a triangle. Okay? It will happen to you. ED and CB. ED is what? No jokes. 12. CB is what? I ask the questions. AD is eggs. And AB is what? Think. Yep, it would happen to you. 5 plus x, very good. So x plus 5. The whole thing's x plus 5, segment addition, right? So, how do you solve a problem like Maria? Well, let's solve for y first, right? How would you get y on its own? Tough question, right? First thing would be flip both sides, right? That would make it a lot easier. When y's on top, it's much easier to solve. How would you solve a problem like that? How'd you get y on its own? Divide. It's already being divided. Multiply by 12. So we do 12 times 12 divided by 9. Now, you don't know what that is, right? But isn't 144 just 12 times 12, right? And isn't 9 just 3 times 3? I bet you know what 12 divided by 3 is. I bet you know what 12 divided by 3 is. What's 4 times 4? I wish you had algebra with me. Playing with your numbers. Simplification sometimes isn't simpler. Which is why I don't like calling it simplifying. I think it's a lie. Perpetuated by the bourgeoisie. All right, y equals 16. Let's find x. Well, again, 9 over 12 equals x over x plus 5, right? I'm just taking these two. Now, if that was a 5 down here, you'd know what to do, right? What would you do? Multiply by 5. Now, it's not a 5. It's this whole thing. So we're going to move it all over by multiplication, okay? So I have x plus 5 times 9 over 12. Okay? If you want, you can multiply that 12 over. Or you can just keep it as a fraction. It's up to you. You want to multiply it over? Okay, let's do that, right? We're allowed to do whatever we want. It's divide by 12, move it over by times by 12. So that's 9. I'm going to put the 9 out front, okay? 12x. What do you do with this? Starts with a D. No jokes. And now we get our x's together. Terrible idea in real life, great idea in math. X is 15. Lots of ways to solve that one.
I missed algebra.
Then you'll love this.
Are you done?
Yeah.
Can you like zoom out so I can take pictures?
Yeah, I'll zoom out.
Stay like that. That's how I'm sitting right now. Really good posture.
I'm Marissa.
Can I see it?
You're like that cat that like sits on the flower pot. It's like this. I do it for the memes. What kind of lines are those? B, E, and AD. What kind of lines are these?
Are you gonna be here after school?
What kind of lines are these?
Give me a hint.
Diana, what kind of lines are these? Katie? Yeah, because they're 90 degrees, right? So, we should be looking for Pythag and potentially similar triangles, right? That's the orthocenter. Remember that breaks it up into similar triangles? Guys, is this a triangle? No, so they're not going to be similar. If I drew the last orthogonal in, it would break it up into similar triangles, right? That would actually be an interesting strategy to use. I won't do it, but it could be interesting because then it becomes a much simpler problem to solve. But whatever. How do I figure out V?
I thought in my head I'd hold my breath until someone gets it.
Katie is choking. It's a right triangle. Can't we do Pythag? Right? Is V a leg or a hypotenuse? It's a leg. So 3 squared plus V squared equals what squared? The hypotenuse squared, which is 5 squared, or 25, yep. The only thing funnier than 24. So V is going to be 4, which makes sense. If you know your special right triangles, 3, 4, 5 is a special right triangle. It's kind of rare to find perfect numbers for a right triangle. Usually it's like weird numbers. Okay, so V is 4. So that's good. Aren't these vertical angles?
Yep.
So that means we've got angle, angle in both these triangles. So that means this triangle is similar to that triangle. So let's match them up. Now, similar triangles have all the same angles, so these must match too, right? So between the red and the green angle is 3. Again, you could write the triangle similarity thing and match up your letters, right? I'm not going to. I'm going to do a shortcut. I'm not going to do what I did last time and then use that to figure out this. I'm going to do a shortcut. Between green and red is 3, right, on the small triangle? What's between green and red on the big triangle? Blue. I know what you were thinking, but that is pretty funny. Is it blue? All right, between red and blue on the small triangle is 4. What's between red and blue here? Oh, we don't know. Okay, fair enough. Probably don't care. What's between green and blue on the small triangle? 5. And what's between green and blue here? Eggs. All right, so I'm going to take these two and solve for x. How can I make this problem easier to solve? How can I make it easier to solve? Katie, shut up. What can I do to make this easier to solve? Flip it. Thank you. Ladies in the back with the dance moves. Now I'm going to flip it. How do I flipped it. What do I do now?
Multiply by 5.
Okay, so I multiply by the top and divide by the bottom. What's 5 times 7?
35.
What's 35 divided by 3? It's 35 over 3. 35 divided by 3 is 35 over 3. Jesus Christ, it's Jason Bourne. Sometimes it do be like that. Like I said, most right triangles have weird numbers for their sides. Let's find x and z. Guys, do you notice the big triangle, triangle ACD, and the little triangle AGE? It is very small, SMOL. They share an angle. So aren't they similar by double angle? They both have right angles and they both have angle A, right? So they're similar. So little guy goes with big guy. So we want to figure out y, right? Y is between the angle we don't know, which is going to be what color? So this is your time, Natalie, right? They already have blue and red. So what must be the leftover color? Green. Very good, right? So y is between green and red. What's between green and red on the small triangle? 3. Z is not part of a triangle. It's not, is it? Z plus 4 is. That's between green and blue. What's between green and blue on the small triangle? Green and blue on the small triangle.
5.
Yeah, very good. They're both the hypotenuses, right? Across from the 90, across from the 90. It'll happen to you. You'll say z instead of z plus 4. Okay? Now, we don't have enough information to solve this, right? Because we have 2 variables, right? We need another one that doesn't have any variables in it. So let's match up. 4 is between red and blue, right? That's on the small triangle, so I put it down below. I did my small numbers at the bottom, right? On the big triangle, what's between red and blue? I want a number. 12. It'll happen to you. You'll say 7. 7's not part of a triangle, right? It's not a side of a triangle. It's a piece of one. Whole thing's 12. What's 12 divided by 4? So all these are going to equal 3 when you simplify. So z plus 4 over 5 will equal 3, and y over 3 will equal 3. What's y going to equal?
1.
Try again.
3.
I times by 3 and get 9. 9! What do I do to solve a problem like Maria?
Ooh, I know. Actually, you multiply it
By 5 and get 15. And then what?
You subtract
4. What's 15 minus 4?
11.
Ta-da!
I have funny game.
Listen to me. You need to understand this. You need to understand this. Mark.
Okay, so I get how you get like y over 3, but how'd you get z plus 4 over 5 and 12 over 4?
Z plus 4 is between the blue and the green angle.
Yeah.
So it's going to be similar to what's blue and green over here. 5, right?
Oh, okay.
Same thing with 12 and 4. 12 is between blue and red on the big triangle, and between blue and red on the small triangle is 4.
Okay.
Be careful with matching them up. If you want to write the triangle similarity statement to match up letters and do CSP, that could help.
Okay.
I was taking.
All right, no more pictures of me right now. I will do funny faces some other time. 11. I told you they're getting easier as we go along. 11 is definitely the easiest. What kind of line segments must those be?
Oh,
Medians. And medians are what to what? Vertex to midpoint. So that's a midpoint. That's a midpoint. And that's a midpoint. What else do we know about medians? 2-to-1 ratio, which means their parts are 2-to-1. The smaller part is always from the centroid or the medicenter, right? To the opposite side. The bigger part is always vertex to centroid. Okay? So if 5's the small part, what's x? It's the big part, which means it's 10. We proved that like 4 weeks ago, but that's a property of the medicenter. That's a property. So on that quiz where we did medicenter, that was one of the things you had to list. Okay? Center of mass and 2-to-1. If this is 6.5 and y is the bigger side, what's y going to be? It's plus 6.5, doubled, right? 13.
Because I'm God. And
I'm going to write this in because it might help. You have to have a big brain play to figure out z. You have to have a big brain play. Aren't these two segments the same? Well, if a point is equidistant from the sides of a segment, then it's on that segment's perpendicular bisector. That's perpendicular bisector theorem converse. So if it's equidistant, then this must be, if it's already the bisector, it must be the perpendicular bisector. It's true. So if that's 90 and that's 90, now we can do Pythag, right? Is y the hypotenuse or a leg? Ladies, shut up. If y is y the hypotenuse of the leg? Good. Because it's across from the 90. So something squared, right? We'll call that a. Plus 5 squared will equal 13. Squared. What's 13 squared?
169.
Very good. And when you subtract 25, you get 144. So what's a going to be?
12.
And if a is 12, and that's 12, what's z? You're praying that one's on there.
I'm gonna take a picture. Wait a second, how do we know which one's the I won't be in here this time. Yeah, you just
X, Y, and Z.
X, Y, and Z.
Mark.
How do you know that the line
Is perpendicular?
Yeah.
Remember, perpendicular bisector theorem says if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of that segment. Remember that? Right? If we have this, then that point will be on the perpendicular bisector. PB theorem converse. All right. The bar is low. Don't trip over it. Do you want to see number 10? Because number 10, I did on the video. If you have questions about it, that'd be good. If you just want to see it, then just watch it on the video, right? The idea is we're going to draw in our parallels and create a bigger triangle, right? We're going to use medial triangle theorem. If you want to use this to abbreviate medial triangle theorem, that's fine. Remember, the black triangle is a medial triangle. We're going to make this a medial triangle. So we're going to draw a bigger triangle around it using parallel lines, right? And then by medial triangle theorem, these sides will be congruent. And then we'll draw a perpendicular bisector in and do alternate interior angles to get that this right here and this right here will be perpendicular. And we do that for all the sides. And then we win. So we draw our parallels, make a bigger triangle, right? So let me do it real quick. We make a bigger triangle with that. Okay, they're all parallel. This parallel to the blue line, this parallel to the orange line, and this parallel to the green line. And then by medial triangle theorem, we know these are congruent, which means these are midpoints. And if I draw in the perpendicular bisector of the big triangle, that creates two parallels with the transversal. So by alternate interior, I get this. I do that for all the sides. And that means they all intersect at K, which we know perpendicular bisectors do, right? Well, if they all intersect here, isn't this line right here that I drew so well, isn't that an orthogonal of the original triangle? And isn't that an orthogonal of the original triangle? And isn't that an orthogonal of the original triangle? Then our orthocenter, or orthogonals are concurrent. Do we have questions about how that's done? Parallels, medial triangle theorem gets the congruency stuff. Perpendicular bisectors, alternate interior. 4 steps. It's on the review. Do you have a question about how it's done? No? Okay. It's a lot of drawing, but it's actually one of the easier ones because it's only 4 steps. Draw your parallels. Use this theorem to say that these guys are congruent, right? Draw your perpendicular bisectors, alternate interior. Therefore, the orthogonals are concurrent. Yeah.
So, but for this one, we also have to like write out our proofs, right?
Yeah, you got to write out everything, right? Yeah. It's a proof. So let there be these lines, right? Call them like point D, point E, and point F up here, right? And do stuff. You'll have to put in these points and K and this point and this point. But it's 4 things. Draw your parallels, call them something, right? Use medial triangle theorem to get a bunch of congruent segments. That's this guy. Right? The Triforce theorem. Okay. And then draw perpendiculars, right? Well, alternate interior. That means this is an orthogonal, that's an orthogonal, that's an orthogonal. And look, they all intersect at K. So we win. We're allowed to assume that the perpendiculars intersect at K because we're not proving that. We proved that actually on the last page, the page I'm going to go to next. And if they're all intersect at K, then the orthogonals do. Yeah.
I like when the other things.
I know. You're welcome for including them. I mean, you can. It's not really a proof.
Yeah, I don't do that.
Okay. Yeah, you want to see number 9? All right, question. What is a Sevian?
A line.
Yes, but what kind of line?
It's like the
Straight line.
Vertex to opposite side. That's a Sevian. Anything from vertex to the opposite side. Is this a Sevian? No, because it's not from the vertex, right? Are perpendicular bisectors Sevians? Are perpendicular bisectors Sevians? No. So we're not going to use Sivas theorem's converse to this. This is the weird one. We're going to draw 2 perpendicular bisectors and then prove the last one has to go through K. Yeah.
So are Sevians and medians the same thing?
Yeah, that's a good question. So Sevians are anything from vertex to opposite side, right? Isn't a median vertex to opposite side? It's just this, right? It's a specific kind of Sevian. So a median is a kind of Sevian. An angle bisector is a type of Sevian. An orthogonal is a type of Sevian. A perpendicular bisector is not. Unless the triangle's like equilateral, because then it will happen to go through there, right? So we're not going to assume that it does, right? Because we'd have to assume this is equilateral. We're not allowed to do that, right? So what we're going to do is we're going to draw in 2 perpendicular bisectors and then prove the last one has to be concurrent. So I'm going to draw a perpendicular bisector here. Boop. Totally valid. You just can't connect it up to the vertices. Don't try to do that. Don't be like, oh, and it's 90. What? No. Okay. So we're going to call that point D and E. I'm going to make this one as well a perpendicular bisector, and I'm going to call it points E and, oh, sorry, I already used E. I always do that. F and G. And where they intersect, I'm going to call K. That's a reasonable assumption, because in order for these to not intersect, those lines would have to be parallel, which means these segments would have to be parallel. And if they were parallel, I wouldn't have a triangle, right? That's not possible. You can't have sides be parallel in a triangle. Does not work. Okay? So, we're going to say let I created line DKE. Ladies and gentlemen, this is important because you're going to get stuck tomorrow about how to write this. DKE. It's the perpendicular bisector of what side of my triangle? BC. I'm going to call it BDC, okay? Do you see how the line I drew is perpendicular to this side? So that's what I'm writing. It's the perpendicular bisector of that side. Cool? This one, the one I drew, that's line FKG. It's the perpendicular bisector of what side of my triangle? AFC. Include the F in there so we know that they intersect. Same thing with the D here. And notice these intersect at K because they both have K, right? So that's my diagram. Now I'm going to prove that this side's perpendicular bisector would also go through K, all right? Now we're talking about perpendicular bisectors. So what theorem do you think we're going to use? Perpendicular bisector theorem. When we talk about the angle bisectors on the page after this, we're going to talk about triangle angle bisector theorem, right? Angle bisectors, right? Make sense? So what is perpendicular bisector theorem? Well, it says that if you have a point on the perpendicular bisector of a triangle, right? That means these guys are congruent. Oh, no. That was a very funny way to address that. So if a point, like this point here, D, is on the perpendicular bisector, then it's equidistant to the endpoints. Do we see that? Okay. So isn't K on a perpendicular bisector? So shouldn't it be equidistant to this guy's endpoints? It is. Let's draw on those lines. Now, isn't K on this perpendicular bisector? So it's also equidistant to these endpoints, isn't it? And that makes sense because K is really the circumcenter, and the circumcenter is equidistant from the vertices. So by perpendicular bisector theorem, AK, BK, and CK are all equal. They're all congruent. Okay. Now here's the thing. Perpendicular bisector theorem converse says if a point is equidistant from the endpoints of the segment, right, then that point must be on this guy's perpendicular bisector. Well, isn't K equidistant from A and B's endpoints? Then it must be on AB's perpendicular bisector. Do you guys see that? If it's equidistant from A and B, then it must be on AB's perpendicular bisector. Goes through K. So by perpendicular bisector theorem converse, do you see how that's the converse? This said if it's on the perpendicular bisector, it's equidistant. This says if it's equidistant, it's on the perpendicular bisector. Okay, it's just backwards. So because it's equidistant, it's on the perpendicular bisector of AB. So I'm going to write that. K is on the perpendicular bisector of AB. Well, if it's on this perpendicular bisector, and this side's perpendicular bisector, and this side's perpendicular bisector, isn't it on all three sides perpendicular bisectors?
Yep.
Well, if it's on all three, they must intersect there.
Yep.
So they're concurrent. Therefore, the perpendicular bisectors of triangle ABC, you do need these little symbols here. It's not just perpendicular, it also bisects, okay? Of ABC are concurrent. That's actually one of the easier ones if you know what you're doing. You draw two perpendicular bisectors and prove the last one has to be. What theorems do you use? Perpendicular bisector theorem and its converse. It's free real estate. Tim and Eric, awesome show, great job. All right, speaking of perpendicular bisector theorem, how do we prove it? How do we prove that D is the same distance between A and C? Well, let's draw in that distance, right? And I create two triangles. What do? How do I prove those two blue lengths are the same? Mark.
You make like the other side of like the 90-degree angle.
Oh, sure. LPT, right?
And then you do shared side.
Yep, shared side. And now by side angle side, aren't the triangles congruent? And if they're congruent, then these two sides are the same. So by definition, D is equidistant from A and C. How do I prove the converse? If it's equidistant, how do I know it's on the perpendicular bisector? Well, this is a little bit weirder. I have to draw in either a perpendicular or a median. It's up to you. I'm going to draw in a perpendicular, and then I'm going to prove those two sides are the same. Well, by the same logic, don't we have HL here, hypotenuse leg? So that means the triangles are congruent, which means these sides are congruent. And if these sides are congruent, aren't these blue lines perpendicular bisectors? So by definition, they are. That's the proof of the converse. If it's the same distance, it's on the perpendicular bisector. If it's on the perpendicular bisector, it's the same distance. Angle bisectors. You're going to use Tabb theorem for this because we're talking about angle bisectors. So of course we'll talk about triangle angle bisector theorem. That's where if you have a triangle that's being bisected, an angle is, then the sides of that will go with the bases. So what we're going to do is, first of all, are angle bisectors Sivians? So we're going to use Sivas theorem's converse to prove they're concurrent. So we draw all three angle bisectors, go around the triangle, and prove it equals 1. Okay? So I'm going to draw on an angle bisector here. I'll call it AD. That divides the triangle into two sides and two bases, right? So AC over AB will equal CD over BD by Tabb theorem. I'm going to do that for all the angle bisectors. Then when I'm ready, I'll go around the triangle. Don't assume they go in here, right? And I'll go AG over BG times BD over CD times CE over AE equals, and I'll substitute, and it'll all equal 1. By Sivas theorem converse, they must be concurrent. I highly advise you to watch the review because we are running out of time. I go through all of these. If you have questions about it, please ask me tomorrow. If you want a head start on part 1 or part 2, actually part 1 tomorrow, come see me before school, and I'll let you start it early. Cannot do part 1 today because I reviewed with you. Sorry.
Can we leave early?
No. How do we prove Tabb theorem?
Triangle angle bisector theorem.
That's what it is. We draw on a line that's parallel to either this guy or this guy, right? This guy here. I chose that one. And then we extend this guy. These two are already congruent because they gave us that. By alternate interior, these are the same. These are vertical, which means these triangles are similar. Since that's an isosceles triangle, these two sides are the same, which means that's x. And since these two are similar, now we can do CSP. A over B equals x over y. Medians, are they Sivians?
No.
Yes, they're vertex to something, right? So they're vertex to something that's a Sivian, right? So when you draw them in, you're going to draw in all three because they're Sivians. And they're going to cut the sides in half, right? And then you go around the triangle and prove that it equals 1. How? Because these two are the same. So when you divide them, what do you get? Times the same thing divided by the same thing. Times the same thing divided by the same thing. So of course it equals 1. Right. What theorem is this? Sivas Converse. Because we're assuming the opposite, just like the diagram is, that they're not concurrent. So what you do is you say, well, if we're assuming the opposite, there should be a line that is concurrent, which means this over this times this over this times this over this should equal 1 by Sivas theorem, right? Because they're concurrent. But here's the problem. Didn't they say earlier that this over this times this over this times this over this would equal 1? That's a contradiction, because that means that this over this equals that over that. And they're not the same, right? They can't be. So contradiction. If there's a contradiction, what we assume was false. We assume that they weren't concurrent. So if we assume they weren't, and we prove that false, they must be concurrent. Sivas theorem's converse is the one you use proof by contradiction, because you assume the opposite, just like the diagram. Bye. You did? Congratulations. I want to hear you play sometime really badly. Yeah? Like you have a YouTube channel or something?
I mean, I can post them.
Okay. Send it to me. Do something. I want to see it. Congratulations. Yo.
I have the slightest problem.
Yeah?
So I'm trying to read books and I have a really strict videos.
Mm-hmm.
What books connect how and
What's the question?
well, it's one of the problem I have is I write books because I'm one the author.
Yeah.
And it's its own universe.
Right.
I need to figure out what books connect why and what planets connect why. Because the idea is, oh, for something my dad